Hi guys, thanks for being early, but can I just get a quick show of hands? Like, how many of y'all have done the problem set for math preliminaries? Like, you can just unmute or preferably unmute, or you can just like give me a reaction or like soundboard if that works. Yeah, I know that at least one of you has done it, so I think that's good. Okay, we'll start at 8. So, yep, just a while more. Oh wait, okay. Yes, come to my attention that you guys are muted. So if you guys have any questions or anything, just message me. Yeah. Okay. So I think we can start. Uh, so just before we start, I'll just do a little quick self intro. So I'm Leroy. I'm from NUSI, and I was part of the A4 team this year. So yeah, I wrote this set of notes for math prelims, and I also like mostly wrote the next set for kinematics. So if you guys have any like questions about these two sets of notes, you can direct them to me. And since you guys are muted, yeah, just message me if there are any questions so that I can see. Okay, without further ado, let's just get straight into it. Wait, let me check that I'm recording. Yeah, okay. Okay. So for math preliminaries, it's basically a collection of all the math that you need to know at the SPhO level. So it isn't very in detail. I think it is I think a bulk of it is similar to what you have seen in your A level H2 math, but there's some probably new stuff that you might not have seen before. So this is probably going to be quite important for doing physics in general as well. So it can be broken down into your limits, your derivatives, which also which also come under your my bad, which also come under your Maclaurin and Taylor series. Then your integrals, and importantly your ODEs or your ordinary differential equations, which are super important in physics. Then there's also a short section on how to manipulate differentials because most of the time when you do physics, you'll be working with differentials instead of like quantities as a whole. And you see what I mean later on when we go through the examples there. Okay, so let's just start with limits. So intuitively, if you have a limit of some function as some variable approaches another value, you can mathematically write it as this, which means that you're concerned with the behavior of fx as x approaches a. So you might be probably asking like, what is the difference between writing this and just writing fa equals to l? So they for most cases in physics, you see this is technically correct, but mathematically speaking, these two are not equivalent because uh these two are equivalent if your function f is what we call continuous at x equals to a, but not all the time your function is continuous. So what we mean by continuous is intuitively speaking, when you draw your function out, let's say you're drawing like some graph here, you draw your function out. a function is continuous if roughly speaking, you can draw it without lifting up your pen or pencil. So you can see that I drew this graph without lifting up my pen or pencil. But if you have a graph like that, uh, if you have a graph like that, then this is not continuous, and your limits actually matter here because there was a discontinuity at this point. There's an asymptote here, and yeah, your function is not continuous there. Okay, so yeah, in English, as x gets arbitrarily close to a, fx gets closer to L. So in general, if your function is continuous, then you can simply just substitute in. So like what you see here in this example, because sine of square root x plus 4 is continuous. So you just sub in x equals to 2, and you just get sine square root 6. This is nothing fancy. So that's like the easiest case of limits that you have to evaluate. Now the next two examples are uh a bit more tricky because you cannot just substitute in 2 in this case. Because if you substitute in 2, you get 2 cubed minus 8, which is 0, and 2 minus 2, which is 0. So that's just 0 over 0. But what does that mean? It's indeterminate. So you don't really get any insights here. And the reason why this is as such is because in the graph of, so if you go plot out this graph, you notice that there's a discontinuity at x equals to 2. And this graph will actually look like a quadratic graph because after you cancel away the factor of x minus 2, you'll be left with a quadratic. But it is the graph of x squared plus 2x plus 4 with a hole at x equals to 2, which means that because it's discontinuous there. So what you do in this case is you simplify x cubed minus 8 using your difference of cubes formula here. Then you notice that your x minus 2 cancels out. Then you're left with this quadratic, which you can substitute in 2, and it'll work out to 12. So in some cases, you have to do this because your direct substitution doesn't work. In other cases, here you have what we call an infinite limit because you're concerned with the behavior as x tends to infinity. But in this case, it's not really meaningful to just sub in infinity here because you sub in infinity, like what does this mean? You don't know what this means, and you don't know what this means also, and you end up with a case of getting infinity over infinity, which also doesn't make sense. But what is helpful in cases of infinite limits is when x tends to infinity, this implies that 1 over x tends to 0. 1 over x squared tends to 0. In fact, your this means that 1 over x n tends to 0, where your n is a positive integer. So why is this useful? You can intuitively see that if you have a number and if a number grows very large, then if you take the reciprocal of that number, it'll be very small. And when that number goes to something as big as infinity, then the reciprocal of that will go closer and closer to 0. So this is helpful because we can do a manipulation by dividing the top and bottom by x squared. Then you get this here. You will get this here. Yeah. And because you didn't change this limit at all, you're just dividing by x squared top and bottom. So as x tends to infinity, you can simply throw away all your terms with 1 over x to the power of something into the 1 over x to the power of something, which in this case means that your this, and this all die out. And you're just left with 2 over 5. And you can't have seen this if you just sub in infinity. In fact, summing infinity is meaningless most of the time. So it is better to manipulate it as such. So these are just some tricks that you might see pop up sometimes. But most of the time, what is perhaps more useful is this thing called L'Hopital's rule. Uh, some some math teachers might not advocate for this because it doesn't promote thinking and it just makes you like do it. So what I mean is that if you have a limit of a form like that and it gives an indeterminate form, an indeterminate form means either 0 over 0 or infinity over infinity or like minus infinity over minus infinity. Anything goes. If you have a form like that, then it just states that you can differentiate your top and bottom and it will be equivalent to the previous limit. So this statement is quite powerful and you can see that using this you can solve examples 1.2 and 1.3 which are illustrated here because differentiating differentiating this you get this, differentiating this you get this. And yeah, you realize that these give the same answers as before. Now the tricky thing about this is that you can only use this if you have an indeterminate form. Sometimes you might fall into the trap of having a form such as uh sometimes you might see forms such as 1 over 0 or let's say infinity over 0, something like that. But are these indeterminate forms? Well, the answer is that they are not indeterminate forms. So if you have a form like that, you cannot use L'Hopital's rule. Instead, most of the time, if you have a form like that, the limit either doesn't exist or you have to do some other funny tricks to get the limit. So in this case, if you substitute in and you get 1 over 0, this actually means that it doesn't exist as the limit tends to infinity. Yep. So just be careful with what an indeterminate form is. Okay. So so far you have seen like some very mathematically involved examples. And you might say that nowhere in physics am I going to get a function such as sine square root x plus 4. Nowhere in physics am I going to get a function such as 2x squared plus 3x plus 1 over 5x squared plus 8. That's not going to happen. And I agree with you. That's not going to happen because these examples are quite contrived for physics. But the main point of getting you to do this is to brush up your limit skills because in physics, most of the time you have to deal with infinite limits as you analyze the behavior of some system as it goes to infinity. You see more examples on this later, what I mean by an infinite limit. But anyway, yeah, main point is get your limits right. Yeah. Okay. Before we see the example, the two famous limits that you should know are these two. So I believe everyone should have seen the first one before, hopefully. The second one might not be that familiar, but you should you should know it. Yeah, because it pops up quite frequently. Uh, one subtle thing is that L'Hopital's rule cannot actually be used to prove these limits. It is circular reasoning. As for why this is true, this is quite mathematically involved. So you can you can look this up in your free time. The way to prove this limits are actually using some geometrical. The proper way to prove these limits is there's some geometrical trick to it, but it's more mathematical in nature. So I won't go through this because we are a physics class. So yeah. Okay. So this was the example that I was talking about. In When we cover oscillations later on, you'll find out that equation of a damped harmonic oscillator. So what this means, there's some big words here. Damped meaning there's a damping force, which can be friction, it can be air resistance, it can be you applying some external force, etc. And this is being applied to a harmonic oscillator, which I think you guys should know because it's just an object in SHM. So if you have such a case, you can solve for the position of this object as a function of time. We will do this in the later chapter, but you realize that general the general solution is of this form, where gamma is some positive constant, which is linked to your damping force. So where do limits come in? If you want to find the behavior of this system after a very long time, which means your t tends to infinity, then you can just take the limit as x, the limit of xt as t tends to infinity, as you have done here. Now, after you do that, you realize that this actually goes to 0. Now, how do you see this? So let's work out this limit. So I can rewrite it like that because e to the power negative that is just 1 over e to the power that. Now, if you are experienced in dealing with limits, you can actually quite instantly see that this goes to 0. Now, what is the reason for that? Your term in the numerator is this term. This is a trig function. Now, cosine is always bounded in this region. Cosine is always bounded between -1 and 1. So you know that this graph, so you know that the value of this cannot exceed 1. But at the bottom you have an exponential function, which as its graph will suggest, its graph looks something like that. Okay, probably steeper. It will go all the way to infinity. So as t goes to infinity, your cosine function is always stuck between -1 and 1. But your exponential function goes all the way to positive infinity, which is why you end up with a case of somewhere between -1 and 1 over positive infinity. And this is what gives you 0 because your denominator goes very large, but your numerator is bounded. So that is how you get to the conclusion that this limit equals to 0. And if you reason it physically, this makes sense because what we are saying here is that after a long time, x tends to 0, and x is the displacement of this object from the equilibrium position. So after a very long time, because you have a damping force, if you have, for example, air resistance, then after a long time, your air resistance would have fully dissipated this motion because energy, the mechanical energy of this moving object is lost over time. So eventually, this object would have to stop moving and settle back to its equilibrium position, which is x equals to 0. So you can see that with limits, you have shown that you have shown that a damped harmonic oscillator will eventually settle back into equilibrium after a long time. So this is one of the most powerful things that a limit can do. In physics, it will be infinite limits, and you have to be familiar with this. So this is just one application. Another application we have is falling with drag. So what we are doing here is we are assuming that an object. So let me Let me draw an object. It's fall. Oops. Yeah. An object is starting from rest. It falls down and it goes here. As it falls, the forces on it, of course, you have your mg, and we are assuming that the drag force on it can be modeled by b times v, where b is some positive constant and v is the speed of the object at that point. So notice how that I've written it as negative bv here. Now the reason is because it is opposite. The direction of the drag force is opposite of mg. So you can show that we can show in a later chapter, which is in kinematics, that the velocity as a function of time for this falling object is has an exponential dependence, negative exponential dependence. My bad. So this is the velocity as a function of time. Then what we're interested here is to find the velocity after a very long time. So when t goes to infinity, that's a very long time. What is v? Which can be settled again by taking a limit here. And we are interested to evaluate this limit. So you want to evaluate this. Now you can take your mg over b out, and as we have seen earlier, when you take a limit as t approaches infinity of e to the power of negative something times t, this term would just go to zero because this is the same as writing 1 over e to the power b over mt, and this will go to a this the denominator tends to infinity, plus this will tend to zero. So now we've established that this tends to zero. The limit inside there is just 1, so this is just mg over b. And this means that after a long time, the velocity approaches mg over b. And physically, again, this makes sense because you guys might have learned of something called a terminal velocity. That is exactly what we're doing here. This is the point where your mg cancels out your drag force. And when your mg cancels out your drag force, your acceleration will be zero. Once your acceleration is zero, your speed or your velocity will be constant. And thus, this is a terminal velocity. So everything here perfectly makes sense with your physical intuition. And yeah, that is the moral of the story for limits. Okay. Uh, any questions on limits before I? Oh, okay. I have a question. Hmm. Okay, so okay, I will address the question in here. Oh, okay. So the question is, why can't we say that? The question is, why is this wrong? Okay, so the reason why this is wrong goes back to circular reasoning. If okay, to be very honest, I do not know the entire geometrical proof, but the proof of L'Hopital's rule, the proof of L'Hopital's rule actually requires you to know this limit. So you cannot use L'Hopital's rule on this limit. This is circular reasoning. Yeah. I can okay, I know a Wikipedia article on this. I can include it later on, but this is quite mathematical in nature lah. So you don't really have to be concerned too much about why you can't prove it this way. You just have to know this limit. Yeah. Yep. Okay. So I'll go back to where I was. Okay. So that's on limits. Now onto derivatives. You should know that a derivative is concerned about how a quantity changes with respect to another quantity. And we'll cover both what we call the first principles and the second principles of differentiation. So the first principle just state this. This is the most formal way you can define a derivative. So a derivative is actually defined using a limit. So that's why you need to know how to value your limits. So this basically, the way to see how this works is you can consider, oops, okay. Yeah. You can consider a graph of some random function. Okay, probably not that straight. Yeah, some random function. If you take 2 points, the graph, let's say you call this x, let's say you call this x, and then you call this a. If you draw the line connecting the 2 points, that will look like that. Okay, let me just use another color. This is the line connecting the 2 points. Now, this line has some gradient, right? So you have some gradient, and the gradient of this is precisely equals to, because this is just x minus a and this is fx minus fa. Yeah, I hope everyone can see this. So once you have this, now you want to think about your point at A as a fixed point. So imagine that it cannot move. Then your point at X, think of it as a point which can move. So now you want to move this point as close as possible as you can to A, but not such that it is at A. So you move this point closer and closer here. And when you do that, eventually, if you zoom in into the graph, you see that this kind of creates a tangent at that point A. And using a limit, we can just write this as which is the mathematical way of describing what I just said earlier. Move the point x as close as you can to A. And we want to look at how this gradient changes. Now, this is how we define the derivative at that point. This is exactly defined as such, which means that the derivative at that point is simply the gradient of the tangent line to the curve at that point. So this is the concept that you need to know. To see how we can apply this, we have an example here. So, oops, okay. We have an example here. We have fx equals to sine x. We want to find f prime of x using first principles. So this just reduces to a case of just plugging in either one of these forms. These forms are equivalent, so you can just use any one of them that you like. Yeah, you can just see that if you plug in this form here, then you expand out this using, You expand this out, then you collect terms like that. Now you have to invoke the two limits, the two famous limits that I mentioned earlier. And remembering that this equals to 0, this equals to 1, this will just simplify it into cosine of x. And of course, everyone knows that d over dx sine x is cosine of x. So that just means that we have done it correctly. And first principles always work. So I would like to stress that first principles always work because that's how it's named. First principles, meaning that it will always work. But most of the time, you won't want to be dealing with such messy limits. For example, if I give you some random function, let's say I give you fx equals to sine cube square root cosine x, something like that. Well, of course, you wouldn't want to plug in. Of course, you wouldn't want to do this, right? Uh, yeah, no one would want to do this. This is a honestly a huge pain to evaluate. While this is technically correct, there are much better ways of doing this lah, rather than using a limit. And that's why we introduce the second principles. So this is probably what you're more familiar with in school. You have your things such as your product rule, quotient rule, and your chain rule, which should be second nature to you at this point. And also these common derivatives, which you should memorize by heart. Uh, I'm sure everyone is familiar with the two columns on the left. I'm not sure if everyone's familiar with this column on the right, but you should definitely try to remember this by heart. Yeah, so that you save some time. So this is what we call the second principles, which basically are your quote unquote derivative formulas. So using this, you can differentiate things like this much easier because it just reduces back to a matter of using your chain rule, your common derivatives. Yeah. So that's why second principles are likely more useful in physics. Now we have another thing here called implicit differentiation. This is quite common because in physics we might not be able to find a neat explicit expression for y in terms of x. So sometimes you might be left with expressions like that. So after you grind through all the math, you grind through all the equations, you're left with something like that. Now, if you ask me, it's extremely difficult to express y in terms of x or x in terms of y because it's just not elegant and it'll be really messy to do so. But if you still want to find out what is dy dx, fret not because implicit differentiation exists. The key of this is you treat y as a function of x, then you use the chain rule. So you can see here that the first step is we differentiated. Oops, why does this keep moving? Okay, first step is we differentiated both sides with respect to x. Then clearly d over dx5 is 0. Now we do the other side. D over dx 2x cosine y plus d over dx 3 sine xy. Now this would be using a product rule. 2 differentiate x keep cosine y, it will be 2 cosine y plus 2 differentiate cosine y keep x. Okay, so we keep x, but how do you differentiate cosine y with respect to x? Now remember that y is a function of x, so you can invoke the chain rule in this case. This will simply just give you minus sine y times dy dx. Now we repeat a similar step for the other one, and you should get 3 cosine xy d over dx of xy which in this case is just x dy dx plus y using your product rule. So this kind of shows you how to deal with d over dx of some function in terms of y. The goal is you always need to fall back on the chain rule and then introduce a extra factor of dy dx basically into the expression. So if you rearrange this, you will get the answer here. Yeah. Okay. Okay. So that is implicit differentiation. Okay. So a common application that you see quite soon in the handouts is how we link force and potential energy. So force is defined as the derivative of potential energy with respect to position. This is how it is defined for a conservative force. Now you see what this means later on in terms of the physics, but it's just a short math exercise here for you to appreciate how differentiation is used. So if you're given any contrived potential energy function, something as contrived as this, although you will likely not have any physical setup that produces this potential energy function. But suppose you're given this, then it's just up to a matter of using your derivatives to find the associated force with this potential energy. Now, once you find force, if you have force, you become very powerful because you can find acceleration if you know the mass. And once you find the acceleration, you can work out everything and you can find the position as a function of time. So this is very powerful. Yeah. Now, the next important application of your derivatives is in your Maclaurin and Taylor series. Why this is important is because they are used for your approximations. And as you guys might know, in physics, approximations are everywhere. So there's this small notation here that I want you guys to be familiar with because we'll be using this notation throughout. So f n x is not f to x to the power of n. It is the nth derivative of fx. Yeah. Okay. So the first thing is the Maclaurin series. This is a series that's always centered around x equals to 0. And this is the general. Why does this keep moving? Okay. This is the general series, and the general term is given as such. So what this means is that if you want to expand any function, you want to find this Maclaurin series up to the nth power of x. What you have to do beforehand is you have to keep differentiating fx with respect to x. You have to do it n times. And after you do it n times, you have to sub in x equals to 0 into each of these derivatives and evaluate uh, all the derivatives at x equals to 0. Then you just sub it into this formula and it will all work out. Uh, one thing to one possibly common mistake is forgetting the n factorial. Sometimes in your haste you might forget this because you're just. But sometimes I understand that you might be obsessed with just working out the f to the power n evaluated at 0. But don't forget this stuff. Yeah. Okay. Then the other thing is the Taylor series. This is a generalized Maclaurin series. This is centered around any x. So you can have x equals to a here, and your general form is just like that. So not much difference from this, just that instead of you're basically just shifting everything by a steps, if you think about it. Yeah. So in physics, you basically never need the infinite form of these two series because what we are concerned about is an approximation that reduces the function fx. You want to approximate fx, which means you want to reduce it to a polynomial. of some appropriate order. And because you just want a polynomial of some appropriate order, you will never need the infinite form. But it is still quite important for you to know the infinite form because sometimes you might not know the order which you have to evaluate the series up to. Now I'll talk more about what I mean by this later on. So with these, there are some common approximations they need to know for sine, cosine, and this 1 plus x to the power of n. This last one is especially important, and I can't stress this enough. The most common form of this approximation you see will be unto the first order, so the one that's in the dotted lines. This is very, very, very common, and you see this a lot when we're dealing with oscillations, when we're dealing with uh actually when we're dealing with almost everything lah in physics, you see this. So just be very just be very aware of this. Whenever you see power a 1 plus x to the power n like that, you should always be thinking, when can I approximate it like that? When can I make it into 1 plus nx? Because you need to be able to spot this form when you're working out your expressions for whatever you need to find, so that you know how and where to approximate. So one common hint the question might show to you is if it says this, x is much smaller than 1. Now if it says this, then this is basically always a giveaway that you have to approximate using using the approximation here. Yeah. Okay, so this remark is what I was talking about earlier. Sometimes you need to consider terms higher than the first non-zero order. What this means is that sometimes, for example, if you're dealing with 1 plus x to the power n, well, most of the time you just approximate it as this. But sometimes, and you might be asking, what are these sometimes? You might need to approximate it to this. So, how do you know which order you have to expand to? Well, the easiest and most straightforward answer I have for you is that you don't. You have to expand it and try first. And this might sound quite silly, but you eventually see that if you expand it to an order that is too small, if you approximate it like that and you substitute it in and you work out the remaining of the math or the remaining physics, you will see that your result will likely not make sense. So I have an example here to illustrate what it means. This example is not in the notes, so yeah. Okay, so you guys might have heard of how we deal with thermal expansion when it is we usually approximate it to be linear. So what this means is that if you have for example, if you have a length, you have a rod, so it is originally of length L naught. Then after some thermal expansion, our formula is like that, where delta T is your change in temperature, alpha is some constant, and yeah, this is your final length. This is what we call linear thermal expansion. Now, most objects you deal with in real life are not 1D. You'll mostly see like either 2D or 3D objects, right? So let's say you deal with a 2D object, some random 2D object here. Let's say that its initial area was A naught. Now, when you heat it by a change in temperature delta T, now you're interested to find what is the final area. Now, let's assume for the sake of working something out first, that it expands linearly as well in area. But except this time, you have a different constant. of beta, and is and beta is not equals to alpha. So how would you find what beta is? So the way that you should work around this is, firstly, area is proportional to length square, and I think everyone agrees with this because you can either see in terms of dimensions, or you can, or it's just logic lah, basically. So what this means is that if you have this for your length, you can apply it to your area. So you can just say, you can say that this is true because area is proportional to length square, and you're just squaring the factor that was multiplied to the length. So nothing no approximations were done to this point. Now this is where the approximations come in. You can choose to expand this however you want. So let's say, but you don't know to what order you're supposed to expand this to yet. So let's say because you don't know, you expand to the lowest possible order you can first. Let's say you expand this to 0th order. Now, in 0th order, this is literally just equals to 1 because you are removing all instances of uh you're removing all instances of x here, which means that to the 0th order expansion, you just get this. But you know that this doesn't make sense because, of course, the area of the sheet is going to change. Now, what this means is that your 0th order is too small, and you approximated it to an order that is too small. And since it's too small, we go to the next order. So the next order will be first order. And since we have this at the first order, so oops, so AF is just this. Now, look at these two equations. This is literally perfect. So what we have concluded from this is that at the first order expansion, beta equals to 2 alpha. And you can see here that without knowing much physics, in fact, but just knowing when to approximate until, you can derive some results from this. Yep. We'll revisit the physics for this later on in thermodynamics, but this is just like an example to show you what I mean by if you approximate to an order that's too small, you get nonsensical results. Because in this case, this result was nonsensical. Yeah. Okay. Now going back to this. So the most common application you see of this is a small angle pendulum. So you can show using Newton's second law that the equation of motion is this. Now, this will be gone through later on in oscillations, but you can just take this at face value first. Now, you see also later on in this handout that if you have a differential equation like this is very, very hard to solve. But the good news is that we are dealing with a small angle pendulum. So theta is always very, very small. So if theta is small, then sine theta is approximately theta. And you can plug this in. Then you get a simplified differential equation, which in this case, you realize that this is much, much, much easier to solve than the first differential equation. Now, you might be asking at this point again, why did we only take sine theta to be theta? Why didn't we consider this? Uh, yeah, why didn't we consider this? Now, reason is because we always are interested only in the lowest possible order. I'll write this out. Lowest possible order where we get insightful physical results. This is the order of expansion we're interested in. Of course, you can argue that if we just didn't expand it at all and we somehow managed to solve the differential equation here, if we somehow manage to solve uh, oops, we somehow manage to solve this equation, then you get the most accurate form of theta as a function of time. And we all agree on that. But the reason why we're expanding is to simplify things. And we are only expanding to the first order in this case because at this order, we will get insightful physical results from this differential equation. In contrast, if you try to expand to, for example, the third order, if you did this, then your equation becomes harder to solve as well. And you won't really get much more insight from that. Yeah, which justifies the choice of doing first order only. Okay. I apologize for the notes moving around. Alright, so that is for differentiation and Maclaurin and Taylor series. I will once again check the chat. Oh, um, okay. Give me, someone doesn't have member roles, so I will. Sorry about this. Okay, yeah. Sorry for that. Okay. Let's go back to this. So yeah, that sums it up for Maclaurin and Taylor series. Key point is know how to differentiate, and when you differentiate to find a series, go to the lowest possible order where you get insightful physical results. Yeah. And with that, we move on to our next branch of math, which is integrals. This is just the reverse procedure to differentiation, and we'll just be focusing on your integration techniques here. So first of all are these common integrals, which all of you should memorize by heart as much as you can. So all of these should be familiar to you, perhaps except this one. So this one is, so the best way to just know this is just memorize it. Yeah, because these are just common integrals. You can just memorize it. Then the common techniques that we use are firstly integration by substitution, which you may just call U substitution. This is how you eliminate parts of your integral to make it something more elementary. So the general rule of thumb, which I always tell people to do, is let U be something in the denominator, or some strange expression hidden in some function. So in general, in the context of physics Olympiad, if you have any non-trivial substitutions or even non-trivial integrals, they'll usually just give you the integral. But in case they don't, you should know how to do some integration. So in this first example, we'll see what I mean by choosing U to be something in the denominator. So I chose U to be exactly the whole expression in the denominator. And when I differentiate it, I get 3 times the expression in the numerator. So using this coincidence, I can simplify the integral as such, and I'll just get 1/3 the integral of 1 over u du. And don't forget to convert back to x at the last step. So sub back your u. Yep. And another one, we have a definite integral here. So you see what I mean here by let u be some strange expression hidden in some function. Uh, so you see that it's quite strange. We have a nested square root. So why not just let u be the strange expression hidden inside the square root? So that's exactly what I did. And with that, you notice that you get something here. But you also realize that uh, from your choice of u, square root x is just this. Which means that you can substitute this back in here and you get that. So this is quite a common trick also. I would like I usually just call this back substitution, where you have written u in terms of x using and then afterwards you have some expression of x, then you write x in terms of u again. So this is what I call back substitution. And once you have that, uh remember to change the bounds of your definite integral here and then sub your u in here. Now the beautiful thing about using back substitution here is that because du dx is this, so dx is uh, okay, dx is this, and this is fully this this side is fully in terms of u. So when you do this and you sub back dx here, you get expression that everything is in terms of u, which means you can just integrate without any worries that there's a hidden x somewhere. And that's exactly what I did here. And you end up after a long time with this result. Yeah. So main two main two things in u substitution that you need to know are firstly letting u be something in the denominator, or secondly letting u be some strange function, strange expression hidden in some function. Yeah. So these are like the two cases you need to spot. So other than u substitution, we also use trigonometric substitution. This is reliant on your Pythagorean identities here, which you guys should be familiar with. So what forms should you spot to use a trigonometric substitution? I've listed the common forms that you should spot here. Now, why do we perform a trigonometric substitution for these forms? It goes back to using these. So let's work out each of them step by step. Suppose you have a form a squared minus x squared. Let, let's say you let x equals to a sine theta. Then this would be just equals to a squared minus a squared sine squared theta to a squared 1 minus sine squared theta, which is equals to a squared cos squared theta. Now, the good thing about this is if your x is equals to a sine theta, then your dx is equals to a cosine theta d theta. Now, this is good because you have this and you have this here. So it is quite likely that you can cancel off one factor of cosine theta, or you can just write everything in terms of an integral involving cosine theta. And that should be much easier to evaluate than having something like that there. So one example could be something like say you have this here. So this for an integral like this, the most intuitive substitution you should be using is a trigonometric substitution here. And yeah, you can work this out by yourself in your free time if you want to. I will skip this in the interest of time. So you can do a completely similar thing for the other two here, except you just be using the other trigonometric identities. And yeah, for the same reasons, it is preferred to use a trigonometric substitution because you can write because you have dx equals to a times something something d theta, and your something something can cancel out with other trigonometric factors in your in these terms in your these terms. Yeah, yeah. So the example here kind of illustrates what I mean by choosing the right form to substitute. So you have this integral here. Now you see that the bottom is uh kind of a mess at this point, but you don't have to worry about it because you can just complete the square and it reduces to this nice form here. Now, what do we do with this nice form here? The first step is to recognize that this falls into one of these forms above, and it precisely falls into the second one. Now, this is literally the second one. So substitute some we can just substitute something involving tangent theta. In this case, we smartly chose x minus 2 equals to 1/3 tangent theta. The reason why we did this is because we want this 9 minus x squared term, 9 times x minus 2 square term, to sort of become a tangent theta term. So the easiest way to do this is by doing this, so that tangent square theta is this, which explains the justification for this substitution there. So the whole point really is to make some term become some trigonometric term by doing a smart substitution. So that is what we did here. And afterwards, it's a matter of working out the math and yeah, not forgetting to substitute back in theta. So uh, to substitute back in theta, sometimes it might be helpful to draw a right triangle with your theta. So in this case, uh, tangent theta equals to 3 times x minus 2. So we have this triangle, and from there you can find your secant theta and tangent theta and substitute it back. So that shows you how to integrate using trigonometric substitution. Now, if all else fails, you may turn to integration by parts. So this is essentially the integral form of the product rule. If you have an integral that can be expressed as a product like that, then you can just apply this formula. Nothing too fancy. Now, the key subtlety here is how you choose these functions. So notice here that I've written fx and g prime x. This These two functions are in your original integral. But since you have a g prime x here and you have a gx on the other side, you will need to integrate this. And since you have an f prime x on your other side, you will need to differentiate this. So you might think that it's counterintuitive because we are still integrating something for this to work. But it really isn't counterintuitive because we are choosing a function such that this is easy to integrate. Because we know that integration is harder than differentiation. So we choose something that's easy to integrate. Then for the other one, we don't really care if it's easy or not. Like even if it's hard, it'll just reduce down to just spamming your product rule, chain rule, and quotient rule, which is nothing fancy as compared to integration. So to help you choose the functions properly, one such guideline that we always use is LIATE or LIATE. This will help you determine what function to choose f for fx to be differentiated. So the priority is as such. So you would typically want to choose log functions first to differentiate, and your least preferred would be exponential functions to differentiate. So this is like a guideline to help you. Of course, I must emphasize that this is a guideline, so there might be exceptions to this now. But in most cases, this should work. So we can see how this guideline is applied here. So we have this integral, uh, oops, we have this integral here. Now, if you just experiment around a bit with using U substitution, trig substitution, you might notice that you don't get anywhere because you have a pesky exponential term and then you have a random sine term. So this will not get you anywhere. And you might then think, okay, I should turn to integration by parts. And you'll be correct to do that. Now, after turning to integration by parts, you choose your functions. So clearly you have two functions here. But how do you know which one to integrate? How do you know which one to differentiate? Well, following the rule above, you have trigonometric and exponential. Trigonometric comes before exponential. So you should be differentiating this and you should be integrating this by the rule. So let's do what the rule does. So using integration by parts, I let fx be the trigonometric function. I let g prime x be the exponential function. So I differentiate it, then I integrate it, and just plugging into the formula, I get this. Now you might think that we are going nowhere with this because we ended up with a very similar looking integral to what we wanted to find, except with a cosine instead of a sine. But don't give up just yet because this example also shows you why sometimes you need to integrate by parts more than once. So now we have another integral here. And since we plan to solve our original integral by integration by parts, and this new integral is so similar to it, why not let's just do integration by parts again? So that's what we do here. And following Liate again, we assign this, then we differentiate and we integrate, and we have this. Now this is perfect because look at what we just found here. This is exactly the same as this. So essentially what we have done here is that we have now a linear equation of the desired integral by using integration by parts. And the linear equation is just here. So now what remains for us to do is just solve this linear equation for the desired integral, and you will get the desired integral as this. Yeah. So this is oh wait, I small errata. Okay. So this kind of shows you how integration by parts usually is done in a way such that you can find useful information. If you choose your functions in a not so smart manner, you sometimes end up in circles or you sometimes just not get any useful information because you wouldn't be able to integrate the function that you chose to be g prime x, or it just leads you to an even greater mess than before. So spotting which functions to integrate or differentiate kind of comes with practice. And yeah, because it comes with practice, I also can't really offer like a full guideline that will solve every single issue. Now, one thing that might be a bit subtle is when you have things such as this. Now, this is not a this is not a standard integral. Uh, so don't be so quick to write this. This is wrong. It is this is correct, but this is wrong. So yeah, don't be so quick to write this. Instead, if you want to solve this, you need integration by parts. But you might ask me, where are the products of the functions? So the thing here is to notice that you actually have a secret one hiding here. So this is just 1 times ln x. So with this, how can we proceed? So we don't know how to integrate ln x yet. So of course, we are not going to set ln x to be the function to be integrated. So we'll set this to be differentiated, and we'll set this to be integrated. So with this, so I would write it as this, which means that you have this, ignoring the plus c here. So by IBP, you will have fx times gx minus f prime x times gxd, integral f prime x times gx dx. And you see that the x is nicely cancelled here, and so you will get this. Yeah, and this is very well consistent with the common integral here. Yep, so that shows you how this comes about. This actually comes about using integration by parts. So yeah, don't forget the existence of the one. Yep. Okay, so that's integration by parts. Uh, an application for integration is found in work done. So this is very similar to the conservative forces idea which I introduced earlier for potential energy. Work done is defined like that. W equals to integral of f dx for conservative force in 1D. So if you just if you are thrown with any random force function as a function of position, then you can always find the work done by this force between two fixed positions. In this case, we have this as an example, and you should try to work out the integral there as an example. But this just shows you how integrals can be applied to physics. There are many more applications, much more than this, but this is just one of the more like elementary ones. So that is all the way up to integration. I will check the chat again. Okay, there's nothing. Okay. Okay, so the last real math part is on ODEs. So these pop up so commonly in physics that you can't ignore them, and you see them basically everywhere. So, uh, so just like a few conventions first. Your I shifted everything. Okay, never mind. Okay, so why these pop up in physics is because a lot of things are non-linear physics, unlike what you do in like algebra-based physics in school. What this means is that a rate, the rate of change of some quantity might depend on the value of some other quantity or the quantity itself. So you may see something like why can't I draw? Okay. So you may see something like technical issues. Okay. You may see something like something like that, or even something like that. So the rate of change of y is dependent on y itself. Now this is clearly non-linear, and you need to know how to solve ODEs in order to find what is y as a function of x. So some conventions we use in physics are prime notation and dot notation. Prime notation is for position, dot notation is for time. So just take note of that while we move on. So first order ODEs, they are always of this form here. So Px and Qx are some functions of x. So we'll investigate some cases here. So the easiest one is if Px is a constant, then we just set Px to be equals to A. So it just reduce to this. Okay, but how do you solve this? The way we solve an equation like this is to always consider what we call the homogeneous equation and then the particular solution. So the homogeneous equation, how we find this is we simply take this equation, we just set the right hand side equals to 0. That's it. That is the homogeneous equation. In this case, it will just be, for this case, you would just get this. Yeah. Now, you have this equation here. So what we want to do is to solve this. Well, the easiest way to do it is just shift things around. And you can always treat dy dx as a fraction. So you can do this. This is what we call separation of variables. So we do this. And now we have this. So our instinct would quite clearly tell us that, okay, we have dy and y on one side, then we have dx on the other side. So why don't we just integrate both sides? And by doing this, you you would get this, where c is an arbitrary constant. So now you have done this, you can proceed to solve for y, which will just be this, where your k is just e to the power c, which is also some constant. And this is consistent with what I've presented here. So you have found this solution by solving the homogeneous equation. This is what we call the, so we can just call this the homogeneous solution. But you might ask, but we treated one side to be 0. So what happens to the qx term in this case? So this is where your particular solution comes in. So for a particular solution, it really just reduces down to a guessing game. You always want to guess a particular solution based on what qx is. So here are some examples of what you want to guess. You can see here that if you have qx as a polynomial term, so let's say qx is a nth degree polynomial, which means your highest term is x to the power n. Then you want to guess a particular solution that is also an n degree polynomial. That's what you want to do. Which means that your particular solution should be of the form be of this form. Likewise, if you have Qx to be some uh, trigonometric term, then you want to guess a particular solution like that. And if you have Qx to be some exponential term, then you want to guess a solution to be like that. So it's quite intuitive how you want to guess a particular solution. You want to follow the form of Qx. And you can see here how I followed the form of Qx. So after you have this guess, you can just plug this guess back into your original differential equation. And after you do that, you will solve for your remaining constants. By doing so, you will find the particular solution. So you might be a bit confused at this point what this means by solve for the unknown constants, then find the particular solution. But there are a lot of examples down the road to illustrate what I mean. So coming back to here, for the particular solution, all you really have to do is guess based on the form of Qx. And after you do all of this work, the final solution would be this. Yup. So as for why this works, well, it works based on some principle which we call linearity, because all these first order ODEs that we're dealing with here are linear. So this means that any linear combination of solutions will give the general solution to this ODE. Well, this might sound quite complicated, but you don't have to know exactly how it works. You just have to know the method to solve the ODE for physics Olympiad at least. So yeah, this is what was presented here. Now in another case, if your px is not a constant, so if it's actually some function of x, then what we have to do here is use an integrating factor. So this integrating factor is always defined as such. So once you once you see this uh once you see this, you should always find your integrating factor first. So it can be shown that once you multiply this integrating factor to both sides of the ODE, you can reduce this into this. If you're unconvinced by this, you can work it out yourself. It shouldn't be too hard to work it out. But especially if you have like a specific px to show this. So once you have this, it is quite easy to do this because you can just shift your dx over here and then you can integrate both sides. And once you do that, you are essentially almost done. You just have to rearrange it a little. So you might have realized that case one, right, where we treated px as a constant, where we had this. Now you might realize that you might think that there's no difference with case two because your integrating factor here is simply just, and yeah, you'll be correct to think so, but there is still a lot of merit in using the homogeneous plus particular solution method. And yeah, we hope that by presenting both methods, you'll be exposed to both of them. So, some examples here. So you want to solve this ODE. So actually, this is kind of a trope because if you manipulate it correctly, you realize that you do not need any of the fancy tricks above. So how are we manipulating this? 3xy squared dy dx plus 8x squared equals to ln x. So just shift things around. And then you divide both sides by 3x. Then you multiply both sides by dx. So you see by doing this rearrangement, all your y's are on one side and all your x are on one side. So you actually don't need any of the fancy tricks above. After you do this, all you are left to do is just integrate both sides and then find the corresponding integrals. Now, all this is left as an exercise for you. You should eventually obtain this as your answer. So, what's the moral of the story here? Why are we showing you this example? So the main thing about this example is when you see an ODE, don't instantly just think and don't instantly just jump straight into thinking, how can I apply integrating factor? How can I apply homogeneous and particular solution? Because sometimes all it takes is just some algebraic manipulation, and you can reduce it to a simple variable separation ODE. In this case, you don't need any fancy tricks. So yeah, just something to be careful before you start bashing out all the integrating factor and all that stuff. So moving on to more legit examples. So we have this ODE here. The easiest way to do this is convert it to the form as mentioned above. We always want to convert the ODE to this form before we start doing anything, which means we should divide everything by x, which means we have this. So the easiest way to proceed here is because px, your px is minus 3 over x. This is not constant. So the easiest way is to use an integrating factor, which is defined as such, and we will get this. So this is your integrating factor. Then again, like I mentioned, you want to multiply both sides of this equation by your integrating factor. Which means you will get which then gives you now, like what I mentioned earlier, you could have jumped from this step to this step instantly. And if you're unconvinced by this, you can work out the derivative here manually, using just some you can just use some product rule and then some chain rule, and you realize that these are equivalent. So once you have this, uh, like again, it becomes a normal separation of variables thing. You just have to integrate it. And yup, you get the same solution as presented here. So yup, so this is how you use your integrating factor. Okay, I will check for any questions. Okay, no questions. Okay, so that concludes first order ODEs. So for second order ODEs, we have it in this form here. And usually for the context of physics Olympiad, we only care for the case where all these things here are all constant. So if they're all constants, then we can just so if they're all constants moving on, we'll just write this. Yeah. So like what we mentioned earlier, the easiest way to think about this is to think about your homogeneous equation and then your particular solution. So your homogeneous equation, which again is simply done by setting right hand side equals to 0. So your homogeneous equation is just this. Then you want to solve this homogeneous equation to get a homogeneous solution. So how do you solve this? Well, the easiest way to do this is actually to make a guess also. So you realize that a lot of solving differential equations is about making guesses. So what is the guess that we want to make here? Well, we want to make an exponential guess of this form. And once you do this, you can differentiate and then you substitute back in. Okay, by this point, you might also realize that your a's cancel out, your big a's cancel out. And because your e to the power of sx can never be 0, so this also cancels out. Then what you're left with is just a quadratic equation for s, which you can solve. And upon solving this equation, you get three different cases. You can either get S1 and S2 are unique and real, S, S1 and S2 are repeated and real, repeated and real, or you can get S1, S2 are complex. So there are three possible cases you can end up with, and we can tackle all three of them separately. So if they are unique and real, this is case one, then the general homogeneous solution is simply that, which means that we just plug in the values of s that we found from this quadratic equation, and then we put it into this form, where a and b are constants to be determined. That's your general homogeneous solution. In your second case, if your S1 and S2 are repeated roots, which means they're equal to each other, that's called S. The general homogeneous solution is slightly different. You see here that you have to multiply by an x here. Now, this might seem a bit weird, like why are we randomly multiplying by an x? But the reason for this is also a bit subtle, and it's included below, is what we call resonance. Now, you don't have to know how it arises again. You just have to remember that if you ever have repeated roots in solving your quadratic equation there, then you have to remember to multiply by an x. You can see that if you didn't multiply by an x, you would you would simply just get. So let's say you just didn't multiply by an x. Let's say you didn't know what to do. You just wrote this. Then this is just no different from writing this. And a, b are constants, so this is just a constant. So it's just no different from writing this. And you can see it can be shown that this doesn't satisfy the differential equation. Yeah. So yeah, your x is important for resonance. Okay, let me just undo this. Okay, okay. Your last case here is for complex roots. So let's say your S is C plus Ti, then your general homogeneous solution instead is given by this form, where you have your cosine and sine come in. Uh, so this can be shown using what we call Euler's identity, which we should have seen. Okay, or more usefully, or like more useful, you can let me just confirm this. Yeah, so yeah, this can be shown using Euler's identity. And by just substituting this S in to your form earlier, which is should give you this, then using this you can get this form of the homogeneous solution. So yeah, again to find the particular solution, you should guess based on the same principles as mentioned earlier. Follow the form of QX and guess, and you will never go wrong. Yeah, and finally you just add them together and substitute in your initial conditions. So some examples are shown here. You for this ODE here, again we use the same guess, the exponential guess. We find a quadratic equation for S, and we solve the quadratic equation. In this case, we have two real roots that are unique, and that's the easiest case. So using your values of S found, you can write this as your homogeneous solution. Now, for the particular solution, this is where things get a bit interesting, because you can be you might be first tempted to guess something as the particular solution being uh c e to the power 2x, because you see here that the right hand side is 18 e to the power 2x. So this matches the form of some constant times e to the power 2x. Oh, so hard to type. Okay. So this is of the same form here. So you might be tempted to guess this as your particular solution. So let's say we just proceed with this. Then we differentiate, and we differentiate again. Then we substitute this back in here. Then we solve. But we realize that somehow we get 0 equals to 18 e to the power 2x with no information on c at all. So clearly something went wrong with our guess. Now what went wrong with our guess is that notice that you are guessing e to the power 2x. Your homogeneous solution contains e to the power 2x also. Now this is what we call resonance. And there's a link here which you can click in the PDF to find out what it is now. But what this means is that if your homogeneous solution has an exponential like that, and you're guessing the same exponential for a particular solution, then it will always lead to some problem like that, where you are not able to solve for your unknown constants. So instead, if you meet a question with resonance, you have to make another guess by multiplying an x to your particular solution earlier. So just multiply an x here. Now, so we can now check with this guess instead. You differentiate again, and you differentiate again, you substitute it in. Now you get C equals to 2. So okay, it makes sense now. So the particular solution can is actually 2x e to the power 2x and not c e to the power 2x. So once you do this, you can combine it together and get your y. So the moral of this story is that when you guess particular solutions, if you find some equation that doesn't make any sense, in this case, this equation, then you know that definitely something is wrong with your guess. And you should go back to your guess and multiply by x or even x squared or higher. And by doing that, you will get the correct particular solution. So again, you don't need to know why this works. You just need to know that it exists and you should remember that it exists. Okay, so some application here, you will learn in circuits about RC circuits where you have a resistor and a capacitor. So if you have a capacitor of capacitance C storing some initial charge Q naught and you are discharging it through a resistor R, we can draw it like that. So yeah, if you have set up like this, then you can show that this is the differential equation that's satisfied by the charge on the capacitor. And this is just an ODE. It's actually a first order ODE, and it's the simplest case that you can have. By solving this, you can either use separation of variables or you can use uh, integrating factor or you can use homogeneous particle solutions. You can get the charge as a function of time, and it's actually negative exponential. Yeah. Again, this can be also an exercise on limits. So going back to limits, as we have covered very early on today, let's say we are interested in the charge of the capacitor as after a very long time. Means we want to take a limit like that. So by doing so, we just plug this in. And again, we see our very familiar form of the limit, e to the power of negative something. And instantly, you should say this tends to 0. And so the charge after a very long time is 0. And going back to your physical intuition, because the capacitor is discharging its charge in the circuit across the resistor. So it makes perfect sense that after a very long time, all the charge on the capacitor is used up, and hence the charge is equal to 0. So this makes perfect physical sense. Yep. Okay. And one last section that is not on math, not on that much math anymore. It's about manipulating differentials. Now, you have to be very comfortable with dealing with infinitesimal quantities and differentials when you're doing physics because they appear all the time. The first concept is know that dy dx is a fraction because we are treating differentials as normal quantities. Above, when we did variable separation for example 1.11, we did this. And from going and by going from this step to this step, we assume that dy dx is a fraction, which allowed us to bring dx to the other side. So actually, unlike what you might have heard from either your math teacher or someone, yes, you are allowed to treat dy dx as a fraction, and we don't care that much about it in physics. So one example is you know that speed is given by the you might know that speed is given by the derivative of position with respect to time. So you can treat this dx dt as a fraction. So if you treat it as a fraction, then you can simply just write this by shifting your dt over. And once you have this, you can proceed to integrate both sides if you wish. So this is what I've talked about earlier. It's called separation of variables. This is very useful if you are given v as a function of time. So let's say you're given v as a function of time, let's say some arbitrary function like this or anything you can put there, then this becomes very useful because you can just integrate this and you can find your x as a function of time using this method. Now, of course, if you treat it as a fraction, you can also apply the chain rule to it. So this is also another arbitrary example. If you're given some random physical setup where you have the mass changing over time, then you have this quantity dm dt, which represents the rate of mass changing per unit time. Then you can use the chain rule to write something like this. So dm dt equals to dm dx times dx dt, because your dx can just cancel out. So we are just technically multiplying by 1 here. But you also know that dx dt is v. So this means that dm dt can be written in terms of v dm dx. So what's the use of this? By using the chain rule like that, it is much more convenient if, for example, you know the quantity dm dx, meaning that you know how the rate of mass changes over distance, but you want to find how the rate of mass changes over time, then this is very useful because you are expressing it in terms of what you know. So the moral of the story here is you can always treat dy dx as a fraction and you can always shift your differentials around. It doesn't matter. Yeah. Another thing Another thing that you should know is how to apply a differential. So what do I mean by apply a differential? So for example, just consider kinetic energy here. I think everyone knows this. But if you want to consider an infinitesimal amount of kinetic energy, what we do is you apply a differential. So an infinitesimal amount of kinetic energy, we will just call it dk. We can apply d to half mv squared. By doing so, we can invoke the product rule, the chain rule, and you can just get this to be dm v squared plus m d of v squared, so half v squared dm plus 2 mv dv, which is exactly what we have there. So this is what I mean by applying a differential. You can you have now obtained the expression for an infinitesimal amount of kinetic energy in terms of an infinitesimal amount of mass and infinitesimal change in speed. And usually these equations are very helpful as it allows us to, for instance, integrate these later once we find other expressions for example, your v and m. So technically, you can write every physical law you know in terms of differentials. And once you do that, you can analyze infinitesimal components of all systems. So what I mean here, we have, for example, thermodynamics. You'll see later on how we write the thermodynamic laws, and we always write them in terms of differentials, almost always. So for example, this is just the first law of thermodynamics. You So you see that it's written in differential form, and you usually always want to write this in differential form as this allows you to set up differential equations, which you can integrate later on. Yeah. So with that, I've covered the content for today. I will. Okay, there's still no questions. So I think I'll just move on to some problems in the last 30 minutes. We'll see what we can cover. So for a show of hands, does anyone want to go through any particular problem, first of all? 2.8. Okay, okay, sure. Okay, so we have this integral here for 2.8. Now the hint that I've given is to manipulate the integrand before even thinking about how to proceed. So what do I mean by this? So the easiest thing that you can see here is that we have something plus something in the numerator, and we have some other thing in the denominator, but that doesn't matter. But when you have something plus something in the numerator, it should hint to you that you can split this into, oh, oh no, okay, big crush. Okay, you can split this into two separate integrals like that. Then with that, you can just deal with each one separately. So you can do a bit of cancellation and cleaning up. Uh, and at this stage, you see that you have two separate integrals. Each one of them is in terms of cosine and sine only. So what we can do is we can evaluate both of these separately. Now, uh, for this one, as what I mentioned, we can use a u substitution by letting u be that something in the denominator. In this case, I'll let u equals to sine x. And the reason why I do this is because I want to cancel out the cosine x at the top. And nicely, we have this. So we can write this, uh, which cancels the cosine x. And then we have 5 over 2 integral of 1 over u squared du, which is just this. C, of course. And we don't forget to put back the x. So this will be this. For the other one, we can do something similar. Again, the rationale is to cancel out the sin x on the top. And this time we have a negative sign here. So just be a little bit careful with that. This will be secant x plus c. So in total, we will have minus 5 over 2 cosecant x plus secant x plus c. That should be our final answer. Yep. So some lessons to learn from this are, at first sight, you might think about how to substitute or like how to do IBP or how to do trig sub, but you should never forget that you can always manipulate the integral before you proceed to make it into a much more familiar form. In this case, by just simply splitting the fraction into two, you can create two simple integrals that are much easier to solve than if you just didn't split the fraction at all. So yeah, just remember that you can manipulate the integral. Yeah. Okay. Uh, any other questions that you guys want to see? Okay, if there are no other questions, I will just go through one more example. Okay, I'll go through one of the ODEs one. Then we'll call it a day for this lesson. Okay, so I will. Okay, let's go through 2.11. Okay, okay. So with this, as always, to start an ODE problem, first consider your homogeneous equation. So you have this by setting your right hand side equals to 0. So you can, I think after a while, you might be able to see that your quadratic equation involving S is simply, you can just go straight from this to this. After a while, you might be able to see this without needing to write the exponential solution out. So this is the quadratic equation that you need to solve. And this will give you complex roots. So when you have complex roots, you always want to go back to what I've mentioned earlier. So recall that if S equals to C plus minus DI, then you have Y equals to this. But in this case, your C is equals to 0. So that makes your life quite simple here. So since your C equals to 0, you can just write uh, and this will be your homogeneous solution. Now, for the particular solution, so now that you know what your homogeneous solution is, you see that both of these are sine 3x and cosine 3x. But your right hand side, which we called the QX, comprises of sine 3x and cosine 3x also. So if you are experienced with spotting resonance, you might see that this is actually a case of resonance. And what this means is that you should be guessing a particular solution of this form, where you multiply by an x here. Now, uh, if this wasn't clear to you, you can you can of course try guessing a particular solution without multiplying by the x. But if you work through the math, you will see that you get nonsensical results. Like what happened earlier with the 0 equals to 18 e to the power 2x case. So as as mentioned, you should always just try to spot resonance as early as possible before you find some nonsensical result and then go back to multiply it again, because it will save you some time working on this out. So now that you spotted this, you can it's quite easy to proceed from here. From here, you just need to find y prime, then find y prime prime by uh yeah, you just need to find these two, then you just substitute it back in. And once you do that, you uh should get this, which implies that and hence your final solution would just be this. So to recall, start with your homogeneous solution by setting Qx equals to 0. Solve for your homogeneous solution by checking which case it is for S, then write down the homogeneous solution. With your homogeneous solution, check whether it is a case of resonance. If there's no resonance, then you can proceed as normal by guessing your particular solution based on your Qx. If there is resonance, then you need to account for multiplying by x or x squared or above to make sure that you get an equation that makes sense. And once you do that, you just have to substitute in your particular solution, differentiate it, and find your unknown constants in this case, and conclude by adding your homogeneous and particular solutions together. That is how you solve your ODEs. Okay. Uh, if there are, if no one wants to request any questions, are there any final questions that you guys have for this topic? All the solutions for everything will be uploaded at the end, like after the other class has also gone through. So don't worry about it if you haven't done it. Yeah. Okay. Then if not, I thank you guys for coming, and yeah, you guys can leave if you want to, or if you want to stay to ask questions, you can also do it. Yeah. Thank you. Thank you.